So what happens now if I'm going to apply a forward bias and reverse bias to this metal semiconductor junction? We are going to see that. So when an external bias is applied, the metal to semiconductor barrier remains unchanged, whereas the semiconductor to metal barrier is either increased or decreased. See, your metals will not have any change when you are going to apply voltage, because the valence band and the conduction band are overlapping and they have a lot of electrons. So from the metal, if you see, metal to semiconductor barrier, that is unaffected because the metals are already having lot of free electrons. But semiconductors will react to voltage, and their functioning will depend on how much voltage you are applying. So the semiconductor to metal barrier will either be increased or decreased depending on the forward bias. So to summarize what is being told here, the depletion region will be common to both metal and semiconductor regions, right? So the depletion region in the metal region will be same. It will be of constant width, it will not change. Whereas the depletion region in the semiconductor side will either decrease when you apply forward bias, or it will increase if you apply reverse bias. So one side is going to be fixed. That fixed side is going to be the metal side, and other side is going to be variable. That variable part of depletion layer is going to be in the semiconductor side. So you know a depletion region in forward bias will be decreasing. What point the depletion region becomes a straight line which is as thin as your human hair. Okay. In the reverse bias, the depletion region keeps on increasing and increasing, and at one point it is impossible for the majority carriers to cross the depletion region because the width is maximum. Same thing is happening here, but only one difference: on the metal side, the depletion region width is going to be constant. On the semiconductor side, the depletion region width is going to be a variable one. That is what you see here. If you see from metal perspective, the metal to semiconductor barrier remains unchanged, whereas the semiconductor to metal barrier is going to be decreased during forward bias and increased during reverse bias. When metal is connected to a positive bias with respect to the semiconductor, the Fermi level of metal is lowered from its equilibrium level. Okay, the depletion region is narrowed and the potential barrier is reduced. The number of electrons are going to be more and more, which are going to diffuse from the semiconductor into the metal. This is going to be forward bias. So under forward bias, what you do? Metal region is given a more positive bias compared to semiconductor region. So if you connect 5 volt to the metal side, you'll be connecting 3 volt to the semiconductor side. So here there is no strictly positive and negative. The condition is metal is more positive compared to the semiconductor. That's it. So because of that, you can see the lowering of the energy levels of your semiconductor. The any voltage you apply, the semiconductor energy levels will lower, and accordingly you see the metal Fermi level will also reduce. Always the Fermi level of the semiconductor will be higher than the Fermi level of the metal. And when these two will be same, only when the current starts flowing, and when the current is going to start flowing, these two levels slowly will try to become same. Okay, so thus there will be a positive current through the device. This condition is called as forward bias. So this diagram indicates the illustration of the energy band diagram in forward bias. In metal side, a slight reduction in the Fermi level will happen when you apply a positive bias to the metal side, and there will be difference between the Fermi levels in metal and semiconductor, giving rise to current. If the metal is connected to the negative bias with respect to the semiconductor, the metal is charged even more negatively than without any bias. The Fermi level of metal is raised. Now we are going to go for reverse bias. So reverse bias for metal, I am going to give negative supply and more negative with respect to semiconductor. So if this is minus 5 volt, okay, and this is sorry, this is minus 1 volt. This is more negative, right? The minus 5, when you compare the voltage level, this is more negative. This is a reverse bias condition. In reverse bias, the Fermi level of metal will increase. So the Fermi level of metal will go up. See here, it is going up. And the Fermi level of the semiconductor will remain at the bottom. So what happens because of this? The electrons cannot go and jump into the higher Fermi level unless you apply some energy. That energy is not sufficient to cross the depletion region. And as you apply more and more negative reverse bias voltage, this Fermi level will go up and up more, which makes it impossible for the electrons to cross the depletion region and go to the other side, constituting reverse bias current. Okay, that crossing the barrier potential becomes very, very difficult. So, however, on the metal side, it remains the potential, the barrier potential remains unchanged. Everything, the change is going to happen only at the semiconductor side. Okay, I'm talking the depletion region width. I have told you in the beginning itself, whatever bias you are going to apply, the variation in the depletion region width is going to be only in the semiconductor side, because the metal side, the depletion region is going to be constant, right? So in forward bias, the depletion region width in the semiconductor side becomes thinner and thinner. The more current is going to flow. In the reverse bias, when I'm going to give the metal a more negative biasing compared to semiconductor terminals, the Fermi level of metal will go up, which is higher than the Fermi level of the semiconductor, which makes the majority carriers uh, impossible to cross the barrier and contribute for current. Unless otherwise you have so much of enormous energy in the charge carriers, they cannot cross the potential barrier. So see here, the barrier on the metal side remains unchanged and limits the flow of current. See, whenever you are going to jump from a lower level to higher level, you need energy. That energy has to be given in from external source. When the source providing energy externally is not sufficient enough, electrons will cannot cross the barrier on the other side. But some electrons will acquire this energy to overcome the barrier, contributing to a very small current called as the reverse bias current. Ideally, we say the current is going to be zero, but practically a very, very small amount of current is going to flow as like a PN junction diode. So that current is going to be happening in the negative reverse bias condition.